Our next topic will be about intermolecular forces, as well as some of the factors that affect the solubility and how we sort of make solutions. All right, so starting with our first intermolecular force, all right, we have London dispersion forces, which I usually denote LD. All right, now London dispersion forces are found in every single type of molecule. All right, these are induced instantaneous dipoles. So what does that mean? Well, that means that let's say that we look at H2, right? We know that it has 2 electrons, right? And most of the time they're going to spend their time around the middle forming that bond, right? But we know that those electrons do get to move around in our various orbitals, all right? And so, right, some of the time we could have the 2 electrons bunched up on that end, or we could have them spread out like this, or we could have them somewhere in the middle, right? Okay? Now, what happens is that here, right, we've got a relatively balanced dipole, and you guys will get to see some of this in lab, all right? But if we have the electrons pushed over to one end, this gives us an instantaneous partial, or a delta, a little delta negative charge on this hydrogen. And this hydrogen, since it doesn't have as much of the electronic charge, right, the charge from the electrons, this is a delta positive. So this one is more negative because we've got those 2 negative electrons, and this one is slightly more positive because it doesn't have those electrons there at that instant. Okay, again, this is an instantaneous dipole. All right, so notice that if we were to draw sort of what our dipole moment would kind of look like, right? It would sort of have those, we'd sort of have a big side with the electrons, and then there's not a whole lot happening over here, right? So again, this side would be delta positive, and this side would be delta negative. Now, as I bring another H2 molecule near it, well, this one's slightly positive. That means that it's going to attract electrons to come toward that end of the molecule instantaneously, right? So just at that instant, right, when this happens to be pushed over that way, this is going to pull that positive charge is going to pull those electrons in this nearby molecule so that it also has a delta negative near this delta positive, and this side would be the delta positive. Notice that now we have a delta positive near a delta negative, and this induced dipole is attracted to each other. Okay, so these 2 molecules with this induced instantaneous dipole, they have an attractive force. All right, so that would be the idea of London dispersion, right? And that's because we again have that induced instantaneous dipole. All right, a little bit of a tongue twister there. Okay, so the next intermolecular force that I want to talk about is the dipole-dipole force. Right? If a molecule has a natural dipole, like let's say HF, right, we know that the fluorine is more electronegative, and so that means that the electrons are going to spend more of their time on the fluorine and less of their time on the hydrogen. Right? So if we were to draw our dipole arrow, right, we have the plus on the plus end and the arrow on the negative end. Again, it's the opposite in physics if you're also taking physics at this time. Okay, but for chemistry, the plus goes with the delta positive side, and the negative goes with the arrow. All right, now when we have molecules that have a dipole already built in, okay, then that means that they are going to have attractive forces and sort of line themselves up such that we have a delta negative near a delta positive, just like in this case. All right. However, for the dipole-dipole, these forces are dictated by molecules that have a permanent dipole. All right. After about so many microseconds, okay, this would just go back to normal, right? They would go back to having H and H, where they all sort of look like that. Okay. This is an induced dipole from its neighbors. This, however, is due to the fact that they have a natural permanent dipole due to the types of elements involved. Okay, so that's a dipole-dipole interaction. The next one that I want to talk about is hydrogen bonding. Now, hydrogen bonding can affect molecules with fluorine, oxygen, and nitrogen bonding in a special way with hydrogens using their lone pairs. Okay, so if I had ammonia, right? Ammonia has nitrogen and it has hydrogens. Okay, well, the hydrogens of a nearby molecule, all right, they can hydrogen bond, okay, to the lone pair on that nitrogen. Oxygen, right, like let's say that we had H2O, all right, oxygen has two lone pairs. That means that it can hydrogen bond with two nearby molecules that have hydrogen, okay, because it has two lone pairs, all right? Now, the fluorine, like let's say that we had HF, all right? I've got HF drawn down there, and we know that HF, it has hydrogens, and fluorine has a bunch of lone pairs, okay? Fluorine can hydrogen bond with three nearby hydrogens. Okay, so these are going to have increasing levels of effect. Okay, so London dispersion forces are pretty weak, dipole are a little bit stronger, and hydrogen bonding are going to be the strongest of these three types of intermolecular forces. We also have ionic forces, all right, which is basically, right, if you have ions, the opposite charges are going to attract and like charges are going to repel. Okay, sort of self-explanatory. Those kind of change based on the ions involved. Okay, so I don't want to qualitatively compare them with the other three, but you can definitely say that London dispersion forces are the weakest, then dipole, then hydrogen bonding in that particular set. All right. Now, why am I talking about intermolecular forces? Well, intermolecular forces play a big role, right, if you're going to be mixing different species together, right? Because let's say that you have two molecules that repel each other, right? Like you have two ionic charges. If you mix two ions that are both positive, they're going to repel each other. That's not going to be a favorable interaction, right? So the energy of your system has to be higher, okay? The lower your energy, the more stable, all right? Now, if we wanted to calculate our energies of mixing, all right, we're going to have to consider a couple different things. Okay, so when mixing, it's going to take energy to spread out or dissolve a solute, right? So if I put salt into, or let's say I put sugar into my tea, like the example from the other day, right? It's going to take energy to spread out those sugar molecules as it dissolves, okay? So we're going to have a positive delta H for that process. It also takes energy to make room or spread out the solvent, okay? So that's going to have a positive delta H, okay? Also, the species, as I was just saying, they're going to be able to interact, okay? If we have a favorable interaction, that's going to lower our energy, so we'll have a negative delta H for a favorable interaction, and it will be positive for an unfavorable interaction, all right? If we wanted to calculate our delta H at mixing, we're going to add up all three of those, such that delta H at mixing is equal to delta H from the first process, delta H from the second, and delta H from the third. All right? That was all on slide 13. Now, some of the other factors we can start with are going to be seen on slide 14, 15, and 16. All right, but I'll go through them one at a time. So, slides 14, right, is where we begin factors that affect our solubility. Okay? The first one is going to be structure effects. Okay? So, for structural effects, polar dissolves polar. All right, this is going to be very important. All right, nonpolar dissolves nonpolar. Okay, or you can always remember it as like dissolves like. Okay, so if you look on slide 14, you see a big molecule of vitamin A. All right, we have double bond, and then we have CH3 and CH3, and all these little nodes are just carbons. I'm just drawing out the molecule. Okay, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have double bond, double bond, double bond. All right, and then here at this carbon we have an OH, we have an H, and we have an H. Okay, now notice, okay, we don't have a lot, right? Remember we had like HH, that didn't have a permanent dipole. Well, these really aren't going to have a significant permanent dipole. So it's not going to be polar except at this OH spot. Okay, so this is the only spot in this giant molecule that has any sort of polarity, right? So this is going to be mostly nonpolar. Okay, so that means that our vitamin A, right? If you remember from biology, your fat-soluble vitamins are A, D, E, and K, right? Well, vitamin A, because it's mostly nonpolar, is going to dissolve in our big, long, nonpolar fat molecules. Okay? So that's why vitamin A is what's called a fat-soluble vitamin. Okay? And it's because it's nonpolar and fat is nonpolar, right? You think about oil and vinegar, or sorry, oil and water, right? Oil doesn't mix with water because, and we know water's polar, so that means that the oil or the fat, right, has to be nonpolar. Okay? Now, water is polar. Okay? Now, vitamin C, right? It's in like every fruit juice known to man, right? It doesn't separate out. You don't have a glob of vitamin C sitting on top of your orange juice, right? Well, vitamin C looks like, oh, I'm so bad at drawing organic molecules. I am not an organic chemist. OH, this is the double bond to an O, this is there, up, over, H, OH, and H. Now notice, in vitamin C, right? Vitamin C, we have a lot more oxygens. Okay, we have a lot more of these OHs, right? Because of that, okay, that means that this is going to be a water-soluble vitamin. Okay, and it's a water-soluble vitamin because it is very polar. We have lots of dipoles in here, just like we have lots of water, or just like we have lots of polarity in our water molecule. So if like likes like, or like dissolves like, right? Polar dissolves polar, so water would dissolve the vitamin C, and nonpolar dissolves nonpolar, so our fat-soluble vitamin dissolves in, so our fat-soluble vitamin, vitamin A, is going to be soluble in our fat molecules. All right? Now, the second effect, right, on slide 15, we will talk about briefly, okay, and that will be the pressure effects. Okay? So in addition to structural effects, we have pressure effects. Now, pressure can alter the solubility of gases. Okay? Now, for gases, solubility increases with increasing pressure. Okay? So solubility of gases increases with increasing pressure. All right? So you can kind of think about that when you think about like your can of Coca-Cola, right? If you increase, right, the pressure in that can is higher than the pressure outside. Why? Because it's holding that CO2 into your Coca-Cola, all right? Or whatever kind of beverage you like. Now, when closed, carbon dioxide is soluble in the liquid when, all right, but when you open it, when you open the can, the pressure drops and the solubility decreases, right? So that gas is less soluble at the lower pressure and it begins to fizzle out. So the solubility decreases and gas escapes. Okay? Now, if the solubility, or sorry, if the concentration is low, and I mean like very low, okay? You can think like the CO2 in gas, or sorry, the CO2 in your Coke, right? Then we're going to use Henry's law, okay? So if the concentration is low, you're going to use Henry's law. Now, Henry's law is an equation that says that our concentration in molarity, right, our molarity, is equal to a Henry's law constant times our pressure, okay? So again, that's your molarity. This is your Henry's constant. And that is your pressure. Okay? That will be an important equation. Right? I want to do just a quick example as our last thing for today of Henry's law. All right? So, that example on the bottom of slide 15 says that we want to know how many grams of carbon dioxide gas are dissolved in 1 liter of carbonated water if the manufacturer uses a pressure of 2.4 atmospheres at 25 degrees C, and the Henry's law constant is 0.031 for CO2 in water. And it's 0.031 molarity per atmosphere. All right, now, in order to do this, right, we're going to use our Henry's law equation. We know that Henry's law is the concentration in molarity is equal to the Henry's law constant times our pressure. We know our pressure and our Henry's law constant, so we have 0.031 moles per atmosphere, molar per atmosphere, and that gets multiplied by 2.4 atmospheres. All right, so that means that our concentration is 0.0744 molar, all right? But it asks for how many grams, okay? So we know that our molarity is defined as moles of solute per liters of solution. Okay, we have the volume, right? We have a liter. Okay, so we know, and we're looking for. So we have our molarity, we have our volume. We don't have our moles of solute, but we want our grams of solute, so we can easily get that, right? So let's get our moles of solute, and that's going to be equal to our molarity times our volume, right? So we have M times our liters of solution, which is equal to 0.0744 molar. We have 2 liters, right, which is going to give us 0.1488 moles, okay? And then we say, okay, we need, this is moles of CO2, and we want grams of CO2, so we're going to use our molecular weight, so we've got 0.1488 moles CO2 all over 1, and the molecular weight of that is 44 grams per mole. Notice that this time I wanted to cancel the moles, so I put my 1 mole on the bottom and my grams on top. That way my moles would cancel. And then this gives me 3.27 grams of CO2. All right. Now, in our next video, we're going to continue with the factors affecting our solubility.